Good afternoon. I would like to thank the organisers for the opportunity to present our dynamic mechanical analysis work on egg tempera paint at this meeting. For this symposium, it fits into the discussion topic concerned with laboratory testing of historical and mock-up samples to inform predictive models. The dynamic mechanical analysis work was performed in the framework of the EU ERA project, Environmental Research about Conservation, and the aim was to develop a risk assessment tool to evaluate the quality of museum environments. And here is part of the ERA team in front of Sander Memorial Chapel in the UK, where some of the dosimeters were exposed. So the purpose and scope of this talk to highlight the findings in the ERA project with particular reference to the use of DMA for evaluating changes in the exposed paint tempera dosimeters, which were found to reflect the quality of the museum environment, and then to demonstrate the application of the recent ACTS thermokinetic software for sparse data using the accelerated light aging data sets obtained from DMA measurements. And here it's appropriate to quote Robert Feller: it's important that the degradation profile, kinetics of degradation, be understood when retarding of degradation is an aim. So here is the project plan of the ERA project. And first of all, the preparation of the tempera films, curing for 3 months, and then the 2 paths for aging: artificial aging or accelerated aging and natural aging, which involved exposure at 6 different museum locations for a period of 9 months. The accelerated aging involved light, which was performed at the Tate Conservation Department, and thermal aging also at the Tate, and then some pollutant aging with mixed NOx SO2 in TNO in the Netherlands. So the samples from both paths were then analysed using multi-analytical techniques. You can see thermoanalytical mass spectrometry and then spectroscopy and XPS. The ERA team was coordinated by Birkbeck College and involved partners for the FOM, my late colleague, Professor Jaap Bon, with whom we had many interesting discussions on the topic, and then Italian partners who were responsible initially for the preparation of what we called the mock painting, and then the site aging. So the site exposure sites which were selected had a range of RH and temperature conditions and light, and here is a summary, and you can see we have controlled conditions in places like Tate in the Claw, which was very controlled, whereas in the Alcazar, the historic castle, we have a very wide fluctuation in RH and also temperature. And here we have the Rijksmuseum close to the Night Watch, and that's better controlled. And this is a storage area. And then we have the Uffizi Gallery. So this is a site. This shows the site of the Alcazar, and here is the paint dosimeter exposed in the Rijksmuseum store. So the preparation, the tempera paint was based on whole egg and mastic, prepared according to traditional recipes and then spread onto Melinex substrate. Melinex was choice of the consortium, but not optimum for our DMA measurements. A selection of pigments was used, including smalt, sienna, so smalt, which is the potassium cobalt silicate, sienna, the iron oxide hydroxide, azurite, basic copper carbonate, lead white, basic lead carbonate, and Naples yellow lead antimonate. So the paint system was deposited on the Melinex using a film applicator, and that's the 200 micrometers wet layer thickness. For DMA, the additional paint was scraped off and enough paint was retained on the surface, and this was clamped in the DMA analyzer. So the distance, so these are the conditions used, and the temperature was scanned from minus 130 degrees to 150 degrees, and the measurement was made at 1 Hertz. So the parameter that we recorded is tan delta, and this is the ratio of the loss modulus to the storage modulus. And tan delta provides a measure of viscoelasticity, and a low value of tan delta corresponds to a more elastic material. So here are some of the results of the DMA curves. And as I mentioned at the start, the Melinex was not optimum, and this is because it has peaks, tan delta peaks, and you can see the black dotted line is the low temperature peak for Melinex, the beta transition, and then it goes up to a transition here. So it's really in this window between minus 50 and 70 that we would measure the response of the paint samples that we were studying. So the unpigmented, you can see, just has a small response there, and the Naples yellow is the red one, and the smalt is the blue. And so basically the presence of this measurable signal is evidence for the formation of a polymeric network, as you can see in the case of smalt and Naples yellow, and to a smaller extent in the unpigmented samples. So for both pigmented samples, it was possible to measure aging effects from the changes in the shape of the tan delta peak and its position. So we also looked at the paint tempera by thermogravimetry, where weight loss occurs with applied temperature program. And you can see that the Naples yellow and the smalt have very small weight loss, indicating there's a high proportion of pigment and low proportion of medium. So azurite and sienna had, in comparison, a higher medium content. So accelerated aging, what changes can we see? So in the 64-day light age sample, and here this is indicated by the red curve, and you can see the change compared to the control sample, which is the black curve. So there is a movement of the signal to higher temperatures with the evolution of cross-linked structures, which are more resistant to temperature. So from the mass spectrometry data, these paint tempera have the presence of oxidized lipids, mastic and polymerized proteinaceous material. So this is what was found. And the effect of pollutant is shown by the red curve. So it shows a decrease compared to the control sample, which is black. And the effect of humidity, and this was 80% RH for 21 days, also showed a change. It shifted it to lower temperatures and reduced the intensity of the peak. This is plasticization by the water molecules. Natural aging also shows changes. So, for instance, if we have the green as the control, red is the change from the light aging, and blue is the change from exposure in the Alcazar for the period of 9 months. And so how did we then go ahead with quantification of this data? So we calculated the ratio values of tan delta at 20 degrees, so at 20 degrees and at 0, and that was after shifting the curves to the same point at minus 55. And so then we plotted the ratio, and here's the ratio of the tan delta values, and you can see there is a gradual increase with light aging, except in the case of 32-day age sample, and the response from the sites is highest for the Alcazar and the Uffizi, and lowest for the Tate. Now the Tate, the exposure was in the claw gallery, which is very well controlled, and this is an uncontrolled site, so it shows that there is a difference in the environment. And we had correlation also with mass spectrometric data, where we see with again for the small tempera, a very nice evolution with light aging, and then a smaller effect for the NOx. And the FOM, this was a control that was kept back at the FOM Institute in an anti-corrosion bag to protect it. And so basically you can see not much difference from the what we get for the 4-day light aged. So and again, the Alcazar has a very strong response. Together here with the sample exposed at Sandham Memorial Chapel, with DMA there was a large variation, so the result is not a very good one for Sandham Memorial Chapel, but we have coincidence there with Alcazar sample giving a large response. And again, the Tate has the lowest response. So that was pleasing. So then the case of azurite, exposure at sites Alcazar and Sandham caused a shift of tan delta to higher temperatures. So black is the control, Alcazar is the green, and Sandham is the red. And here we made a slightly different calculation. We took the ratio at 6 degrees and minus 10. So again, a ratio of tan deltas, but at slightly different temperatures. And we find a large response for Alcazar and a very large response for Sandham. Unfortunately, this was only measurements were only performed once, and so there could be some. Yes, and the data here are normalized to the light aged to the control. In Sandham Memorial Chapel, we have this uncontrolled environment, and here we can also see that there are temperature and RH gradients across the painting. So we have differing conditions in the front and at the back in terms of relative humidity, and differing conditions front and back with temperature. And so this is something that we need to consider then when we consider microclimates. And then the effect on the dosimeters. With lead white tempera, we had problems because very few samples gave a measurable signal, And so we did get some information from the control, light aging, and then this light blue one is exposed at the Tate. But the site exposed at Uffizi and Alcazar showed a very small peak, and the paint had become quite brittle, and the adhesion between the paint and the Melanex was not so good. So given the low values for Alcazar and Uffizi, the peak shift was measured to evaluate the change. And so there's the peak shift. And again, Alcazar comes out to have a higher peak shift, and Uffizi than the Tate, which is a more controlled environment. And again, we see some correlation with the mass spectrometric data. So the Alcazar has a high response together with Uffizi, whereas Tate has a lower response. And here we see actually the exposure of these paint dosimeters by Stephen Hackney and Joyce Townsend in the Claw Gallery. With Naples Yellow, we also saw a difference between control and light age sample. And here we took peak ratios at 20 degrees and -8. This is the Melanex response. And so the ratio 20 to -8 again showed a high response for Alcazar, Uffizi, and a very low response for the Tate. So you can see some had there's quite a large standard deviation in some cases. So basically it probably, so that's something to consider. So the summary of changes in accelerated light age paint temperatures normalized to the control, I've plotted those, and you can see that if we normalize it against the control, we see the evolution goes more strongly in the case of the Naples Yellow and possibly the Smalt compared to the Azurite. And I was intrigued. I thought of using this recently acquired software, AKTS software, for lifetime prediction and using the values that we obtained on light aging. Here, the lower diagram shows where site age samples are included, and values for lead and cobalt temperatures are also higher, except for Sandem, where Azurite is higher than Smalt. So AKTS software, so what can we do with that? So essentially it requires at least 20 experimental data points collected at different temperatures. So this is the requirement. And so we were at a disadvantage because I didn't have different temperatures. So I considered then the condition of light aging, and we had different levels of light aging, so I took that instead. And basically from the data we should be able to obtain the kinetic models, and then statistical analysis can rank these kinetic models, and from that we can get a long-term lifetime prediction with confidence intervals. So let's see what we obtained. So this is the data that I included. So the days of aging, so control 4 days, 8 days, 16, 32 and 64, and the temperature, of course, one temperature and one humidity, and I took the values of the peak ratios. And of course, it restricts the models that can be selected, as you can't actually calculate an energy of activation from this. So, however, I could obtain some information, and basically we have a plot here of reaction progress with time, and it showed differences in aging profiles between smalt and azurite temperas, which I had seen already from the plot of the peak ratios. So once this model was entered, then a further calculation for lifetime prediction, and these prediction bands with confidence limits of 95%. And so basically it's predicting the values for the ratios after 1 year and up to about 2 years. So the smalt tempera, the peak ratio after 2 years was within those values. Azurite, the peak ratio after 2 years is lower, and Naples yellow is similar to the smalt. So basically indications are similar to what has been observed. We want to follow this, we want to do more with this software. Anyway, recommendations for DMA post-ERA project. The substrate could be changed to optimize measurements by DMA. So though Molecunex was used in this project, more traditional supports of wood and canvas with their preparation layers could also be used, e.g. primed canvas samples. And here's an example of aging studies on primed canvas samples. So unaged, and then 22 months later, 17 days heat and light aged, and 34 days heat and light aged. And the temperature was 70 degrees for the thermal aging, and RH was 50%, and light exposure was 18,000 lux. So you can see that unaged and then 22 months later, those are the curves. This is for the storage modulus, and with the tan delta, you can see the shift in tan delta to higher temperatures. So with 34 days heat and light aging, there is a very large shift in that direction. So very suitable for aging studies. Another examples of aging of resin mastic on substrate Nomex, and resin mastic was later used as a coating on PQC quartz resonators for microclimate monitoring in museums. And this gives you the plot on the right-hand side shows the profile of change expressed through the frequency shift of the crystals at different locations. So basically, again, the Alcazar, the Cord Room, uncontrolled environment, and you can see a big change, whereas something like the British Library, which is very controlled, the response is much lower. And also the PET, the blue, the Petrie Museum is uncontrolled, so the uncontrolled have different and higher responses, and also Rangers House English Heritage. We've also measured 19th century paint composites and tested the effect of RH. And in testing the effect of RH, we coated the sample with this oil formalin so that it didn't lose moisture during heating. And so here's the effect of, say, no conditioning with no formalin, and the red is the red is no formalin, and black is no conditioning but with formalin. So this oil didn't make much difference to the measurement. After 3 months at 80% RH, you see a noticeable reduction in the softening of the modulus with temperature, and after 24 hours at 96% RH, a further decrease in temperature. And this is shown as a shift to lower temperature in tan delta. So that's the effect of RH. So conclusions, DMA, even with challenging substrates such as Melanex, can provide useful information on effective artificial aging and natural aging at sites. Changes in peak shapes can be quantified, and that information correlates with chemical data from mass spectrometric techniques and reflects environmental conditions at the sites. Small amounts of data from past accelerated aging studies have provided some information using AKTS sparse data software. Future work will involve measurements made at several temperatures so that the software can be used as it's intended. It has wide applications in determining shelf life of materials, for example, vaccines. This work can be of some value to current paint tempera studies, and there have been some very interesting papers on this topic, and here's one of them. So thank you very much, and thank you again for the kind invitation.